So let me see. Let me make sure. Testing. Let me see. I'll go here. Captions. Testing. Testing 1 2. Testing. There it is. Okay. All right, greetings, scholars. I don't know where your classmates are, but we have at least one person here, so we're going to go ahead and get the party started. Again, these sessions are recorded. I am recording attendance. The attendance is recorded through coming into the Teams call. So, at the end, all I do is see who showed up, when they showed up, and when they left. How long were they here for, right? And I use that to base attendance. With an excessive amount of unexcused absences, then you can get booted and it can affect your money. So we'll have to track down the other students to see where they are, and they're going to be responsible for this content. Let's see. So I think the goal for this week, I think we just had one other section that we needed to work on. Last time we worked on section 1.2. So today all we really need to do is section 1.3. As usual, if you have questions about anything, feel free to unmute yourself or type in the chat to get my attention. If you email me and I haven't responded, best thing is just to either text me on my office cell phone number or just ask me during class. I get an inordinate number of emails, so I tend to become numb to them. So the best thing is either to text me on my office phone or just ask me during class, okay? And again, if you have questions, feel free to either unmute yourself to get my attention or type in the chat. I am monitoring the chat, okay? So, oh no, let's go back. So today we're going to be working on section 1.3, radicals and rational exponents. Let's just kind of see how it unfolds. Okay. A few learning objectives here. Evaluate square roots. Use the product rule to simplify square roots. Use the quotient rule to simplify square roots. Add and subtract square roots. Rationalize denominators and use rational roots. So what if I told you the math you're about to dive into isn't just theoretical, but an essential part of navigating the complexities of your everyday lives? Have you considered the hidden role these concepts play in your budgeting decisions, the algorithms driving your favorite apps, and the scientific breakthroughs you may one day contribute to? Join me as we explore section 1.3, radicals and rational exponents, unveiling the captivating connection between these mathematical ideas and the dynamic world that surrounds your terrestrial journey and future endeavors, right? So, it seems like the stuff that we talk about is like so abstract and disconnected, but these concepts are the underlying architects or underlying like conversations behind pretty much all the processes that we use. You can't do construction without doing calculation and measurements and using these kind of calculations. The apps that we use, the way we communicate, the cell phones that we use, the TV that we watch, the cars that we drive, and they all use these mathematical concepts to operate, right? And so what we experience as consumers, right, emphasis on the word consumers, is just the end product. We don't see the underlying conversation. We don't see the underlying calculations at play, right? So what we're doing here is diving into some of these hidden conversations that are going on. And hopefully maybe we can like pique somebody's interest, right? And if not, it's okay, right? But that's essentially what's going on here, right? So the first concept that we want to look at is evaluating square roots, right? A square root, right? A square root is going to be the inverse of squaring, right? Like if you consider 4 squared is 16, so then 4 is the square root of 16 because 4 squared is 16, right? So it's the inverse. A lot of techniques in mathematics uses inverses, right? The inverse of addition is what? Subtraction. The inverse of multiplication is what? Division. So the inverse of squaring a number is going to be taking the square root, right? So squaring the square root of a number brings you back to the original number. For example, if you square 4, where you have 4 squared, then you'll get 16. And the square root of 16 is going to be 4. So the square root function acts as the inverse of squaring, similar to how subtraction undoes addition, or as the inverse of addition. To undo the squaring operation, we use the square root, right? Okay. And I think that these are the first of these videos, right? I don't have these pre-recorded. So I am using our sessions going forward into the future, right? So I'm trying to make these as official as possible and clean as best I can, because I intend to use these for years to come, right? These conversations. Principal square root. The principal square root of a is going to be the non-negative number that when multiplied by itself equals a. It's written as a radical expression with a symbol called a radical over a term called a radicand, right? So you have the square root symbol, that's called the radical, and the radicand is the thing inside the square root, right? And the whole thing together is called a radical expression, right? And as always, if anything is not clear, feel free to unmute yourself to get my attention. If you ever connect with your classmates, I think it's a good idea to like start a group me. I usually encourage all of my students to start a group me, and that way, if you need help, you can ask it. I encourage collaboration. I just need each person to really submit their own work, right? We get unlimited attempts at all assignments. You can submit any assignment past the due date. The system is set to take your highest score. The only caveat is if you're submitting an assignment late or using a late pass, then there's a 5% late penalty. So the highest you can earn is a 95%. But I think that's golden. Again, all assignments, all homeworks and quizzes are already posted for the entire semester. You can access them right now. A few things that you don't have access to, I think the exams are scheduled for release, so they're not available right now. They have staggered release scheduled dates or whatever. And then the recorded lectures, again, I'm making them as we go. This also applies to my asynchronous course, so I'll pull a copy of this and make it available for them as well. Because it's the same content, it's just an alternate delivery style, right? But I'm proud of myself. This is my first time making my own PowerPoint slides. Usually I pull them from the publisher or some other sources or whatever. I was like, you know what? And I know the structure, the underlying structure of how they build them. So I was like, okay, well, let me just make these. So I took some time today to actually make my own PowerPoint. I'm happy with how they turned out. They're actually working. They're really basic, right? But I'm just happy it's working, right? So let's look at this example one. Evaluating square roots. We're asked to evaluate each expression. Okay, this is simple enough. Let me grab this. Okay. Okay. So evaluating square roots. For instance, let's work on part A here. So the square root of 100, right? Well, 100 is a perfect square, right? So 100 is what? 10 squared, right? So the square root symbol cancels the squared symbol. So this symbol cancels this symbol, essentially. We really should put an absolute value, but for right now, we're just going to go with this. So then this leaves us with 10, okay? Let's look at B. Now we have the square root of 16. So square root within the square root. So let's just take it one step at a time, piece by piece. Let's start with just the square root. Oh, welcome. We have another person that's finally found us, all right? So good. I'm glad you guys are finding your way. With the tennis, I understand like for the first few sessions, it's a struggle kind of getting used to the rhythm and finding the course, finding our meetings or whatever. So, it's okay. I'm not going to be super, super strict on the tennis. As long as you show up within like the first week or two, then, but if it's an MIA, if people are like MIA and I can't find you, I don't see you at all, then I don't have any other choice. As long as you show up, I was like, okay, don't worry about the first few sessions. I'll mark you as excused for those and we can keep moving forward. So with the part B, what we're going to do, we're just going to focus on just the square root of 16 by itself, right? So square root of 16, well, 16 is a perfect square, right? So that's the same as what? 16 is what? 4 squared, right? So this symbol cancels this symbol. So that means we're really just working with the square root of 4. Well, 4 is a perfect square as well. I'm going to kind of move down here a little bit. Now 4 is what? 2 squared. Okay. And again, I really feel like because of that squared symbol being on the inside, it forces it to be a positive number. We should be using absolute value, but we're just going to kind of go with these results as is. All right. So they cancel. So it looks like the final result here is 2. Okay. All right. Let's continue working over here for part C. And so for our people, oh, we got more. Welcome. So these sessions, this is our second official session. If you missed last class, don't worry about it. I'm okay marking you as excused, as long as you kind of finding your way within like the second session or at least by the third session. You know, I don't make a big deal about the first ones. These sessions are recorded. You can pull a copy of the recording in Teams, right? So in here inside the chat, you can find the previous recording and this one. I also load them to my YouTube channel. My YouTube channel is called Beautiful Mind Pfeiffer. I also put some links to my YouTube in Populi. Anything that you see me writing, you will receive a copy of. I posted a link in Populi. It says like daily PDF lectures box link. You can find a copy of these there. So when I finish class, I load a copy there. And then also, if you're just joining us, all assignments are available. I gave their instructions on how to access the homework assignments in My Open Math in the syllabus. But homeworks and quizzes for the entire semester are available right now. You can get ahead. It's just a bit challenging because my recordings are not ready yet because I'm making them as we go. But you can, if you want to like study the book and go ahead and homework, you can. And we'll be, you know, there's a schedule, there's a tentative schedule in the syllabus, right? So all homeworks are available, all quizzes are available. Exams have a staggered release date. I'm creating the PowerPoint lecture slides and the recordings as we go. And I think that's the meat and potatoes, right? Okay, so let's see. And as we kind of go through the presentation, if you have questions, feel free to unmute yourself to get my attention or type in the chat. I am monitoring the chat. All right. Okay. So if we're working on part C, we have the square root of 25 plus 144, right? So we can't cancel the square root across that plus. So let's just go ahead and simplify the radicand, or simplify the inside of the radical first, right? So 25 plus 144, what is that? 169, okay? So this is really the square root of 169. And I think 169 is a perfect square, all right? Just take a moment to yourself to see if you can think about that, right? So 169 is what? 13 squared, right? So that's the same as the square is 13 squared, right? So again, square root is the inverse of square, so they cancel each other out. Just like addition is the inverse of subtraction, multiplication is the inverse of division, square root is the inverse of squared, right? So this symbol cancels this symbol. And this leaves us with 13. Okay? All right. And then for part D, we have the square root of 49 minus the square root of 81, right? So we can work each square root individually and then subtract our answer. Notice that what? 49 is a perfect square, right? So we got lucky with these. 49 is what? 7 squared. 81 is what? 9 squared. Again, square root and square root are inverses. So this symbol cancels this symbol. This symbol cancels this symbol. Okay. So then it looks like we're just working with 7 minus 9. And it looks like the final result is -2. Okay. All right, so we got 10, 2, 13, and -2. All right, let's see how do we do. 10, 2, 13, and -2. Okay. All right, let's keep going. So using the product rule to simplify square roots. The product rule for simplifying square roots, if a and b are non-negative numbers, the square root of the product ab is equal to the product of the square roots a and b, right? So here, we're looking at the square root of a product is the same as the product of the square roots, right? So because we're doing multiplication, keep in mind that division is another form of multiplication, right? If we were to do divided by 2, dividing by 2 is the same as multiplying by a half, right? So keep in mind that division is another form of multiplication. So because we have multiplication inside the radical, we can break that radical up into 2 radicals, the first factor times the square root of the first factor times the square root of the second factor, right? So the square root of the product is the same as the product of the square roots. Okay. So let's see. So how to. Given the square root radical expression, use the product rule to simplify it. Factor any perfect squares from the radicand. Write the radical expression as a product of radical expressions and then simplify, right? So this is how we would use this. You know, if we were taking the square root of a product, simplify the product within the radical, write it as a product, and then split it into the product of radicals, right? That's kind of a mouthful. I feel like when we work a few examples, it'll sink in a little bit better. People, how many people we got? See all. Okay, we hold it strong. We got Three Musketeers, the Trinity, the Holy Trinity, holding strong. Each session we get more and more people, so that's a step in the right direction. All right, let's look at this example too. Using the product rule to simplify square roots. We're asked to simplify the radical expression. Okay. So let's start off with part A. We have the square root of 300, right? So now 300 is not a perfect square, but it is a product. It's something times something else, right? So 300 is what? 3 times 100, right? So that's going to be the square root of 3 times 100. So then if we go ahead and apply the product rule, we can break this square root and we can break this square root of a product into the product of two square roots, the product of square roots, right? So long story short, we can break this up into the square root of 3 times the square root of 100, right? But 100 is a perfect square, right? So now we're back to example 1. So this is going to be the square root of 3 times square root of 100 is what? The square root of 10 squared. This symbol is the inverse of this symbol, so they cancel. So then it looks like we're left with 10 times the square root of 3. Notice that I put the 10 in front of the square root because if I wrote it like the square root of 3 times 10, you know, you might be tempted to say, oh, is that 10 inside of the radical? It's kind of ambiguous, right? So whenever possible, you know, we will use the commutative property of multiplication and put the number in front of the radical. Do we have more people? See you all? No? Okay, we're good. That's okay. All right. So I've intentionally moved the 10 in front of the radical, so it's clear that the 10 is outside of the radical. Okay, let me, I'm just going to strike through this. I'm going to just erase it. It's fine. Okay, so we got a result of 10 times the square root of 3. So this is the result we got there. Okay. My table is like extra squeaky. I can't make a move without it going. Give me just a moment to get some water. Ooh, 162. Now, when I look at 162, I know 169 is 13 squared. So 162 is not a perfect square. Let me write out the factors of 162. So I'll do that to the side. So then if we say like 162, well, I know it's 2 times something. What is that, 81? Oh, and 81 is a perfect square. So we're Gucci, right? I'm going to move this, shrink it down just a little bit, and just like move it here. Okay, let's try that again. That's a little bit better. Okay. So now we're working on B. So we're going to break this apart. Now we want to, for the variables, we want to try to get perfect squares. In other words, even powers, right? So that 162 we said was what? 2 times 81. Now that a to the 5, let me write it this way. A to the 5 is what? A times A times A times A times A, right? We have 5 A's, and B to the 4 is 4 B's, right? Since we're doing square roots, we're looking for groups of 2, right? We're going to identify groups of 2, right? So the first one, that first 2, you know, is not a perfect square, so it stays, right? Stays as a square root of 2. Square root of 81, by now, you should be able to see that that's a 9. So let me just do this for now. Now, with the variables, we're looking for groups of 2, right? So here's one group of 2. Here's a second group of 2. Here's a third group of 2, and a fourth group of 2. So each of those groups of 2 counts as a whole number on the outside of the radical, right? So we're going to have one A here, a second A. That lone A stays as the square root of A. I'm going to rearrange a lot of this. And then we have a B and a B, right? So if we simplify and rearrange it, things that are outside the radical, I'm going to move to the left. Things that are still inside the radical, I'm going to keep on the right, right? So we have 9A squared B squared times the square root of 2A. See here, 9 is there. It came from the square root of 81. A times A is A squared. B times B is B squared. And then this A is still in the radical, and that 2 is still in the radical, right? So that's what we got. Again, if anything is not clear, feel free to unmute yourself to get my attention or type in the chat. I am monitoring the chat. Let's look at the prepared notes and see how do we do. We got 10 times the square root of 3, 9A squared B squared times the square root of 2A. 10 times the square root of 3, 9A squared B squared times the square root of 8. Okay, factor perfect square from the radicand, right? So anything that was a perfect square, they grouped them together, and then anything that was not a perfect square, they left it to the right. Square root of 81 was 9. Square root of a to the 4 was a squared. Square root of b to the 4 was b squared, right? So we saw 2 different ways of arriving to the same conclusion, which is, normal, right? Like, anyway. Oh, also, just as a random thing, if you would like a free activity to do on this weekend is a second Sunday at the High Museum of Arts. So it's free admission, right? The second Sunday of every month is free admission at the High Museum. It's just something free to do. There's free parking right outside of the High. It's just a matter of finding a space. Just on Sunday, just on the Sunday or whatever. Yeah, another student was like, it's also MLK weekend, so I was like, yeah, I just try to alert students of the free admission at the High. It's just something fun to do that's free, right? Okay. Ooh, that would be a good grand prize. How many times could I do that, though? I can't do that too often. Okay, let's keep going. So, given the product of multiple radical expressions, I use the product rule to combine them into one radical expression. So, I think in the previous, we had the square root of a product and we broke it into the product of square roots. Now, we're going to have the product. We're basically doing the reverse. We have the product of square roots and we're going to combine them into one radical. Okay. So, using the product rule to simplify the product of multiple squares, simplify the radical expression. Okay. Now I'm a fan of, instead of getting the bigger numbers, let's simplify it down first and then combine it, right? Because the 12, even though in the form it's in right now is not a perfect square, it has a perfect square in there because 12 is what? 4 times 3, right? So what I'm going to do here, we got this square root of 12 times the square root of 3. Well, 12 is what? 4 times 3? Oh, all right. And then we actually generate another perfect square, right? So the square root of 4 is 2. Uh-oh. Did you die on me? No. So here, we have the square root of 4 times the square root of 9, right? Well, I guess we could have gotten a bigger number. The square root of 4 is the perfect square. That's 2. The square root of 9 is a perfect square. That's 3. So this result is 6, right? Now, the text, more than likely what they did, 12 times 3 is 36. And then you can see, 36 is a perfect square. So the square root of 36 is 6. The reason I avoided that is because sometimes if you multiply it out initially, the numbers get ridiculously large, right? So even though I knew that wasn't the case here, but I'm like, I just didn't want to start a habit of multiplying and getting these bigger numbers. I'd rather break them down to the smaller numbers and work with the smaller numbers I feel like my chances of making mistakes are reduced when I'm working with smaller numbers than with large numbers, right? If that makes any sense. We are like breezing through this. I don't know if I made this long enough. Okay. And again, all the stuff that you see me writing, I'm going to make a copy available in my box link. Again, you can access that link and populate once we're done. And you're going to be able to find a recording of the session in 2 locations, either here in Teams inside the chat, but I think it expires after like 120 days. I do intend to pull a copy of this recording and load it to my YouTube channel so my asynchronous team can, my asynchronous students can use it as well. So then we have the quotient rule for simplifying square roots. It says the square root of a quotient A over B is equal to the quotient of the square roots of A and B, where B is not 0, right? So just like where we have the square root of a product became the product of the square roots, well here it's the same concept. It's just instead of it being multiplication is division. So when we have the square root of a quotient, it can be rewritten as the quotient of the square roots, right? So we can break it apart. So given the radical expression, use the quotient rule to simplify it. Write the radical expression as a quotient of 2 radical expressions, and then simplify the numerator and the denominator. Okay, I feel like that's not too bad. So using the quotient rule to simplify, right? So given this, I mean, okay. So we're starting with 5 over 36 like this, right? So if we apply the quotient rule, we can break this quotient into the quotient of the radicals. In other words, we can break this into the square root of 5 divided by the square root of 36. But we just saw where the square root of 36 is a perfect square. So the top stays as is. Square root of 36 is 6. Okay, and I think we're good here, like this. I'm going to change it up. So those little lines you saw me doing, that's just a way for me to highlight the final answer. Sometimes I put my final answer in a box like this, and sometimes I use those lines that you saw. Right. So it's just a way for me to have a copy of the original question and for my final answer to jump off the screen. Okay. So using the quotient rule to simplify an expression with 2 square roots. Simplify the radical expression. All right, this one has a lot going on. Okay, looks like 13 is in there. So let me start by getting a copy of the original. Now on top, we have this 234 x to the power of 11 y. Okay. And on bottom, we have 26 x to the 7y square root. Okay. So let's combine these 2 separate radicals into 1. So we can rewrite this as 234 x to the 11 y over 26 x to the 7 y. All this one expression inside the radical. Now it looks like 234 probably divides by 26 evenly. Siri, what's 234 divided by 26?
234 divided by 26 is 9.
9, right? Okay. So this is going to be, we know we have a 9. We have x to the 11 divided by x to the 7. Now, I think last class, right, we said that if we have x to the 11 divided by x to the 7, we're going to subtract those powers, right? So that's going to be 11 minus 7, which is 4. So that's going to become x to the power of 4. A number divided by itself is 1, so these guys essentially just cancel. And I think we still have our square root, which we haven't taken yet. So now we have perfect squares. The square root of 9 is what, 3? So when we take the square root of an even power, we just cut the even power in half, right? So the 4 becomes a 2. Okay, hopefully this makes sense. Hopefully we're all aboard and we're not all aboard. And if you have questions, again, feel free to unmute yourself to get my attention or type in the chat. I am monitoring the chat. Okay, guys, let's keep moving. Kendra, Sharnitha, ladies and gentlemen, let me not be one-sided, right? Yeah, I think we're multiple genders here. Okay. 3x squared, okay. So adding and subtracting square roots. We can add and subtract radical expressions only when they have the same radicand and when they have the same radical type, such as square roots, right? So it's similar to like how we add and subtract variables. It's like when we say combine like terms, it has to be the same variable with the same power. Well, the same thing applies here. We just look at the radical kind of like the variable. It has to be the same radical with the same radicand and the same type of radical, like square root and square root, cube root with cube root, and stuff like that. It basically has to be combined. Long story short, it's combined like terms, right? So for example, the sum of the square root of 2 and 3 times the square root of 2 is going to be 4 times the square root of 2. However, it's often possible to simplify radical expressions, and that may change the radicand. The radical expression square root of 18 can be written with a 2 in the radicand as 3 times the square root of 2. So the square root of 2 plus the square root of 18 can be rewritten as the square root of 2 plus 3 times the square root of 2 to give us 4 times the square root of 2. So given a radical expression requiring addition and subtracting of roots, we simplify. Simplify each radical expression and then add or subtract expressions with equal radicals. So the takeaway here when adding and subtracting square roots, the real concept is combine like terms. It has to be the same radical with the same radicand and the same type of radical, right? Let's see it in action. All right. So notice the first radical is the square root of 12. The second radical is the square root of 3, right? So in that form, we can't add it, but maybe we can manipulate that first one to match the form of the second one, right? So put it in a form where we can add, right? Okay, let's start by getting a copy. So we have this 5 times the square root of 12 plus 2 times the square root of 3. Now 12 is what? 4 times 3. So this is going to be the same as 5 times the square root of 4 times the square root of 3 plus 2 times the square root of 3. Okay. But the square root of 4 is what? 2. So then 5 times 2 is going to be 10 times the square root of 3 plus 2 times the square root of 3. So now we combine like terms. We have the same radical with the same radicand of 3 and the same type of radical. They're both square root, right? So we have a square root of 3 and a square root of 3. So 10 plus 2 gives us 12. 12 times the square root of 3. Okay. Hopefully that made sense. 12 times the square root of 3. Okay. Subtracting square roots, right? The same concept as addition. Basically, the main takeaway is combine like terms. Let me kind of remind you all that. So with attendance, it does monitor when you guys show up and when you leave, and I do factor that into attendance. Like if I see that you really weren't here, I might be inclined to not give you full attendance. You don't want to play that game. Honestly, I'm just going to be frank with you. Like, if you just log in and just kind of be chill, I don't really make too big a deal about it. I don't really single people out because it's a waste of time and energy. So as long as you're here, and then if you zone out, I'm not going to make a big deal. I just need to see that you all are here. Now, obviously, I want you to engage and ask questions. That's in an ideal world, but I'm doing what I got to do to make myself available and keep my sanity, right? Because in the past, I used to get irritated with that. I was like, hey, come on, I'm asking this question, blah, 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 right? So then I realized, I was like, okay, this is remote. It's not like if we were in front of each other, I could just like look you in your eyes and be in your face, right? But since we're remote, it's a little bit different rhythm and energy. I could still press it, but, I just don't have the energy for that, right? So I just kind of keep a record. I just kind of log what you all are doing and then, make assessment based on that, right? So, so just be careful about coming and going. The simple thing is just be here about 5 minutes early, log in, and just let it run until the class is over, right? Now, obviously, I might ask questions. You might miss out on extra credit opportunities. It is best to be engaging and listening and be present, but at a minimum, just relax, right? Just relax for the time of class, if you can, right? Now, obviously, sometimes we have technical issues or whatever, and then that's another case. That's something else, right? But I'm just saying for the sake of saying. Okay, subtracting square roots, right? Let's start by getting a copy of the original. we have a 20 square root of 72 a cubed b to the 4c minus 14 square root a cubed b to the 4c. Are they the same? Almost. Now, 72, what is that? Is that 9 times 8? 9 is a 3, and 8 has a 2, so 6, 36. It looks like that's 36 times 2, right? Okay. So we're going to do the following. So the perfect squares, we're going to put the perfect squares on the left. Anything that's not a perfect square, anything that's left over, we're going to kind of leave it to the right, right? So the 20 persists. Now 72, I think is 2 times 36. So the 36 is a perfect square. There's a 2 over here, right? I'm going to move this around a little bit. Now, a to the 3 is not a perfect square, but we can have a to the 3 can be rewritten as a squared times a, right? B to the 4 is a perfect square, and c is not a perfect square, right? So we can say this radical times this radical. So that's how, I know that was a little bit different, right? But that's how we're going to approach it. Let's see if we can do something similar with the second expression. So then we have the 14. Now 8 is not a perfect square. 8 is what, 2 times 4? So the 4 is a perfect square and the 2 is not. A to the 3. A to the 3, we're going to break apart into a squared times a, right? So we got an a squared here and the a here. B to the 4 is a perfect square and c is not. Okay. Okay. So let's simplify these perfect squares. Now we got a 20. Square root of 36 is 6. Square root of a squared is a. Square root of b to the 4 is b squared. And then what's left over looks like the square root of 2ac. 14 persists. Square root of 4 is 2. Square root of a squared is a. Square root of b to the 4 is b squared. And again, we have this square root of 2ac left over. If we combine like terms, let's see. 6 times 2 is 12, so that's 120. AB squared times the square root of 2ac. 14 times 2 is 28. AB squared times the square root of 2ac. Okay. So we have like terms. Notice we have AB squared times the square root of 2ac in both terms, right? So then it's just going to be 120 minus 28. That's 100 minus 8, which is 92. So there's going to be 92 AB squared times the square root of 2ac. Okay. So that one was a little bit more involved. Once upon a time, I saw this poster when I was a student. It said, there is no such thing as complex. What we consider to be complex is just a long string of simple ideas, right? I feel like this example is case in point, right? Because if you look at it in and of itself, it's very daunting and it looks complex. But really, if you just break it down into the simple components, it's just a long string of simple ideas. All the simple ideas we've been talking about today just kind of put together in one example, right? So if you've understood the previous examples that we've done today, now we're just doing them in one example. If this one gives you trouble, then you kind of need to go back and work a few more examples of the previous ones, right? If that makes any sense. Okay. So again, what we consider to be complex is really just a long string of simple ideas. Okay. Hopefully that's okay. Let's keep moving and grooving. Okay, we are moving right along. Let me see. Did we get that one? Uh-oh. We got our numbers off. 20. Oh, 20 times 3. 36. Let me see. 72. Is there more? I think there's more. Wait a minute. That's definitely not the end. Oh, I'm missing the answer there. Yeah, oh no. Okay, let me see if I can go pull it. Yeah, that's definitely missing some more. Oh, it just wanted it to leave those. Give me just a moment. Let me see. I'm gonna pull this one up because that 8 there are perfect squares all up in there. But I think they wanted it to leave it as a cubed b to the 4. I mean, okay, that's probably the case. Let me check something real quick. I want to pull this up real quick and just confirm. If I go L, this is OpenStax. Oh, also there's a PDF copy of the book in Populi as well. Subjects, math. This is algebra and trig. I just want to view it online. Go to the book. We're in section 1.3. I want to go to example 7. 2, 6, 7. Show and hide. Okay. Okay. So yeah. Okay. So we kind of went a little. We went above and beyond, right? We went a little further than we needed to. We could have stopped at the 8a cubed b to the 4 times c, because then you'll have the similar expressions. You can argue for either one, right? So we're just gonna stand by our answer because 8 has a perfect square. There are perfect squares in there, right? So we're gonna just kind of let that one be for now. So rationalizing denominators. So at least in one example, I know we had like a square root of 5. We had a square root in a fraction, right? Typically, when our final answer, we don't leave square roots in the denominator. So if we had finished with like 2 over the square root of 3, we usually don't leave square roots in the denominator, right? So we use this technique called rationalizing the denominator to remove the square root out of the denominator, right? So when an expression involving a square root radical is written in simplest form, it will not contain a radical in the denominator. We we can remove radicals from the denominators of fractions using a process called rationalizing the denominator. So given an expression with a single square root radical term in the denominator, rationalize the denominator. Multiply the numerator and the denominator by the radical in the denominator and then simplify, right? So we're asked to write this expression in lowest or simplest form, right? So let's give it a go. Okay. So let me start by getting a copy. We have this 2 times the square root of 3 over 3 times the square root of 10, right? So now the 10, it can be broken apart into what? 2 times 5, but there are no perfect squares there. Let me write this a little bit better. That's kind of sloppy. It's still sloppy, but I think let me do this. 10. That's a little bit better. Okay. So again, usually whenever we leave a radical expression, we don't leave radicals in the denominator, right? So to rationalize this, in other words, to remove the radical from the denominator, we multiply by 1 in the form of a square root over a square root, right? So we multiply the top and the bottom by the radical in the denominator, right? Because if we multiply by 1, it doesn't change our answer, it just changes the form, right? So we're going to multiply by 1 in the form of square root of 10 over the square root of 10, right? Because something divided by itself is 1. 1 times anything is itself. So this doesn't change the answer, it just changes the form, right? So now on top, we're going to have 2, 3, 5, right? 2 times the square root of what, 30? On bottom, we're going to have 3 times the square root of 100. But the square root of 100 is 10, right? So you can also look at it like this. 3 times the square root of 10 squared, right? Notice square root and squared, those symbols cancel each other out. They're inverses of each other. So this symbol cancels this symbol. So 10 times 3 is 30. 2 times the square root of 30 over 30. Okay? Again, if anything is not clear, feel free to unmute yourself to get my attention or type in the chat because I am monitoring the chat, right? Okay, so notice so this is equivalent to the original expression, and we no longer have a square root in the denominator. Right? Okay, let's keep going. Wait a minute. Oh, yeah, we can go further, right? Because 30 is a multiple of 2, right? So we can simplify that even further. I totally missed it, right? So 30 is what? 2 times 15. And we have 2 times the square root of 30, right? So notice we have all multiplication and division, so we can cancel. We're not trying to cancel across addition and subtraction, right? Because we can't do that, generally speaking. So because we have all multiplication and division, this factor cancels this factor, and we're left with the square root of 30 over 15. I'm going to shrink this down to size just a bit. Just because I can. Okay. All right, not too terribly bad. I'm doing the best I can to not mention the time. I feel like if I keep mentioning the time, it's going to make it draw out. But I noticed it. So when we're still kind of far out, I just kind of leave it. And I know it's late. You know, I'm like, I tried to eat before. I definitely took a nap, so that's the only reason I have energy. I had to take a nap before class, but I tell you. And I spent most of the day kind of putting this PowerPoint together, so like I said, I'm happy about it. Given an expression with a radical term and a constant in the denominator, rationalize the denominator. Find the conjugate of the denominator. So the conjugate is going to be that number such that when you multiply it by it, you're able to get rid of the radicals, right? Like if we have, you'll see it in action. You'll see it in action. I multiply the numerator and the denominator by the conjugate, use the distributive property, and then simplify. So write this in simplest forms. Okay, so let's see. So the conjugate in this case, because the denominator is 1 plus the square root of 5, the conjugate is going to be 1 minus the square root of 5, right? And you'll see that when we FOIL it out or multiply it out, the radical is going to be gone. All right, so let's see it in action. Okay, so on bottom we have 1 plus the square root of 5, and on top we still have the 4. So again, we're still going to rationalize by multiplying by 1. We're going to multiply by 1 in the form of the conjugate over the conjugate, right? So the conjugate in this case is going to be 1 minus the square root of 5. 1 minus the square root of 5. Okay? So now on top, it looks like if we distribute that 4, right? If we distribute the 4, we're going to get 4 minus 4 root 5. And on bottom, we have to FOIL, right? First, outer, inner, last. So first times first is a 1. Outer times outer is minus the square root of 5. Inner times inner is plus the square root of 5. And last times last is going to be minus the square root of 5 squared, right? A number plus its opposite, these guys together add to 0. The square root symbol is the inverse of the squared symbol, so they cancel each other out. 1 minus 5 is a negative 4, okay? So on top, we still have this 4 minus 4 square root of 5. On bottom, it looks like we have a negative 4, okay? So I'm going to factor out 4 from everything. On top, if we factor out a 4, we're left with 1 minus square root of 5. On bottom, if we factor out a 4, we're going to have 4 times a negative 1, okay? So the 4's cancel. And then if we divide by negative 1, we can essentially just, divided by negative 1 is the same as multiplying by negative 1. So we can distribute that negative, right? So if we distribute the negative, looks like we're going to get negative 1 plus the square root of 5. Okay, that takes practice. It's, to me, it's simple, but it's not easy, right? The concepts are simple, but it's not easy because, you know, we all have different backgrounds. We all have different things going on right now. You know, it's going to take some practice. So again, I know at one point I encouraged you all to do a group me. Also in Populate, I think I posted some information that potentially could work on accessing free tutors, right? So you definitely want to connect with the tutors. You can make use of my office hours. My office hours are Tuesday and Thursday mornings from 9 to 11 in Teams. If you log into my office hours and I'm not there, just send me a quick text to my office cell phone and I'll hop on. Yeah, I don't necessarily log in exclusively, but I am available during that time, right? And I'm usually just sitting at a desk or whatever. Okay, so here we got -1 plus the square root of 5, right? And that's the same thing, right? It's a commutative property of addition. Okay, I am tired of talking, but we're almost done. Yeah, yeah. We don't have that much left, so let's just keep going. Let me pause for the cause. Man, this water tastes good. So I'm having like a weird experience, right? Like I go to this like health food store to like get water. They have like alkaline water. But as of late, I noticed that it kind of tastes like a little bit metallic, right? I was like, it just don't feel right, right? So I don't know. I had this stroke of genius. It was like, hey, get a Brita water filter and just filter it. So the water that and the water is like really cheap. I mean, it's not expensive. That's the only reason I do it. It's supposed to be alkaline, but people lie or people, whatever, right? So if I take that water that tastes a little bit metallic and run it through the Brita filter, it don't taste metallic anymore. Like it tastes smooth and clean, and it's like enticing. I'm like, yo, that's wild. And so like the Brita filter is really just like carbon, right? Carbon is supposed to be like the ultimate absorber. It can absorb toxins out of the body. I mean, it's great for like water filtration. Now, I'm not saying like go get some dirty water from outside and run it through a carbon filter and you're good to go. Obviously, there's more filtration things that need to happen, but for whatever I was experiencing when I took the water that I had and I ran it through the Brita filter, it tastes it changes the texture and the taste. It doesn't taste metallic. It makes it smooth and it doesn't have that metallic taste anymore. And I think I got the idea because I saw some little Snapchat or a TikTok or something. They were talking about taking vodka and running it through the filter, and they were talking about or some kind of like alcohol, running it through the filter and showing how it changes the taste. Right. So I thought it was interesting. I haven't tried that, but they were like, yeah, it changes it. It makes it taste better. Right. And I haven't tried it. Right. But I have tried it with the water, and it's like night and day. And so, it's weird that the water has different tastes, but it does. I am the king of distractions and procrastination. I love to go into like alternate stories. Sometimes they're relevant, many times they're not. Um, so I'll do the best I can to stay focused and stay on task. But again, we're almost there. We have 10 slides remaining. If we run out of time, more than likely, I'll release you all and finish the recording because I do plan to use it going forward, right? So using rational roots, although square roots are the most common rational roots, we can also find cube roots, fourth roots, fifth roots, and more. Just as the square root function is the inverse of the squaring function, these roots are the inverse of their respective power functions. These functions can be useful when we need to determine the number that when raised to a certain power gives a certain number. So principal nth root. If a is a real number with at least one nth root, then the principal nth root of a, written as the nth root of a, is the number with the same sign as a that when raised to the nth power equals a. The index of the radical is n, right? That's a mouthful. I feel like let's work a few examples and it'll sink in. So here we're asked to simplify each of the following, okay? Now 32 is a perfect power of 5, right? Because I think 32 is what, 2 to the power of 5, okay? So with part A, because the index is 5, we're looking for groups of 5. Let me say that one more time. For part A, because the index is 5, we're looking for groups of 5. Every time we get a group of 5, that counts as one whole number on the outside. All right? Okay? So for part A, we have the fifth root of -32. Okay? This is going to be the same as the fifth root of, I'm going to write it as -1 times 1, 2, 3, 4, 5, right? We have 5 2's. So in this case, we're looking for groups of 5. Sorry, that's supposed to be a 2. Right? So that's going to, on the outside, that's going to serve as just a 2. The fifth root of a negative should just be negative. Right? So the fifth root of -1 is -1 because -1 to the power of 5 is -1, right? I think that's how that goes, right? So then ultimately this should be -2. So our claim is that if we say -2 to the power of 5, we should get -32, right? So hopefully that makes sense. Let's try another one. Okay. So for B, again, the index is 4, so we're looking for groups of 4, right? So we're going to go ahead and combine these and factor out these numbers, right? Write them in fully factored form. So we're going to have a fourth root. Now 4 is 2 times 2. 1024. Siri, what's the square root of 1024?
The square root of 1024 is 32.
So 1024 is 32 times 32. So it looks like that's 2 to the power of 10. Siri, what's 2 to the power of 10?
2 to the 10th power is 1024.
Okay. So 1024. Okay, so I'm not going to write all that all the way out. So instead, what I'm going to do, 4 is 2 squared. 1024 is 2 to the power of 10, right? So then we can add these powers? We can add these powers. So this is going to be the fourth root, 2 to the power of 12. Okay. I'm going to jump ahead. So now, another way we can visualize this. Whenever we have like these alternate indices, like square root, like in this case, we're dealing with a fourth root, we can rewrite the radical as a rational power, right? So when we say the fourth root of 2 to the 12, that's the same as 2 to the power of 12 divided by 4, right? So the denominator of the fraction there is the index of the radical. Again, we can rewrite this radical as a rational power. So now we can see that, 12 divided by 4 is going to be 3. So that's really just 2 to the power of 3, which is 8. Okay? So that's going to take some getting used to. I am running out of space here. Copy, paste. Okay. All right. So then we're working on C. Let me make sure we still got it. Okay. So let's work on C. Now we got this negative cube root. We got a cube root. On bottom, we have 125. On top, we have 8x to the power of 6. That's a cube root, and it's negative. Okay. All right. So this is the same as the cube root of, now 8 is 2 to the power of 3. We have x to the power of 6. 125 is 5 to the power of 3. Okay. So if I rewrite all of these as rational exponents, this is going to be a negative 2 to the power of 3 over 3, x to the power of 6 over 3, divided by 5 to the power of 3 over 3. Okay? So then that's a negative 2x squared divided by 5. Now, hopefully, we'll see if the book does this. Oh, did I lose my thing? Maybe the book does it a different way. We'll see in just a moment. Okay. Let's work on part D. Okay, we got this 8 times the 4th root of 3 minus the 4th root of 48. Okay. Let's manipulate that second expression, that second term. 8 times the 4th root of 3. Now we have the 4th root. Now 48 is what? 6 times 8. So 8 is 2 times 2 times 2. 6 is 2 times 3. There's our group of 4 that we were looking for. Okay. I'm running out of space here. I'm just gonna shrink this down for right now. I'll resize it in just a moment, or I'm just gonna move it and I'll adjust it a little bit later. I know it's a little bit jarring right now. So now we have 8 times the 4th root of 3. On the outside, this is going to be 1, 2. So minus 2 times the 4th root of 3. Now we have like terms. They have the same index with the same radicand. So now we can say 8 minus 2 gives us 6 times the 4th root of 3. Let me paste. And let me resize this so we don't have all that overlay. And I'm going to expand it as large as I can. So that seems to be about what I can do here. Okay. Okay. Let me see. So the 5th root of negative 32 is negative 2 because negative 2 to the power of 5 is negative 32, right? I think we said that at one point. So in part B, they went on and expanded. They said the 4 times the 1024 to get the 4096. You know, again, I personally don't like to work with those big numbers. So you saw the way I did it. Not to say that my way is the easier way. That's just what makes sense to me. And I'm trying to be as simple as possible. What they did is simple, but again, sometimes working with those large numbers can get complex, right? It can be a little bit overwhelming. All right, I think for part, yeah, okay, so for part B, they broke them apart and then simplified, but I think we got that same result. And then for part D, we got the same thing. Okay, we're gonna let that be. So radical expressions can also be written without using the radical symbol, right? So this is what we were just doing. I just jumped ahead and used this because I felt like it was a little bit easier. So radical expressions can be written without using the radical symbol. We can use a rational or fractional exponents. The index must be a positive integer. If the index n is even, then a cannot be negative, right? So we can't take the even root of a negative number. We can also have rational exponents with a numerator other than 1, right? So yeah, I think that's okay. Rational exponents are another way to express principal nth roots. The general form for converting between a radical expression with a radical symbol and one with rational exponents is given as here. You see where we have a to the power of m over n. That's the same as the nth root of. You can either do the nth root of a to the power of m, or you could do the nth root of a quantity to the power of m. Right. Generally speaking, these two forms are the same. It changes when the n is even, right? If the n is even, then one of them has to be a square root. An absolute value. This one's going to have an absolute. It just changes when the n is even, and we'll see it in action, and we'll catch it as it comes. Okay, I'm going to let you kind of read that how-to on your own, just because we're kind of short on time. Write this as a radical and simplify. Okay. So we have 343 to the power of 2/3, right? So we can write this as a radical. Let me see. I feel like it would be easier to take the cube root first. Let me see. 6, 7. Siri, what's 7 to the power of 3?
7 cubed is 343.
Okay, so let's take the cube root first, all right? Because it just seems like it'll be more simple. So we're going to do the cube root of 343 quantity squared. So we just realized that the cube root of 343 is 7. So then this final result is 49. Okay. You see it there. Okay, let's try another one. Write this using a rational exponent. Okay. So we're starting with the 7th root of a squared under 4, right? So let's focus on the denominator. Let's rewrite the denominator as a rational power. So that's going to be what? A to the power of 2 over 7 under 4. We might need to rationalize. We might need to multiply the top and the bottom by a to the power of 5 over 7. So that way the radical leaves the denominator. We might stop here, but just in case, I'm going to write this other part. So to rationalize, I'm going to multiply by 1 in the form of a to the power of, hang on. Yeah, because when we add, it should be 5 over 7, right? 5 over 7. Right? And I chose this form of 1 because if I say a to the 2 over 7 times a to the 5 over 7, we add those powers and it should give us 7 over 7. Right? And that way it's just a on the bottom. So now on top, we're going to have 4a to the power of 5 over 7 over a. It's either the second point or this one. I'm going to go with this. And if we may have done too much here, but let's see. Oh, okay. They just want it as a negative power. Okay, well that's fine. Yeah, because usually, again, that negative power is leaving a radical in the denominator, but that's fine. So it was neither one of them. They wanted it as a, yeah. I'm not gonna stress too much about that. Let me just get rid of this because it's not wrong. They just didn't care about leaving a radical in the denominator in this case. So we got the rational exponent, and then they just wrote it, moved it up, right? So a negative exponent flips the fraction. So then we would say 4a to the negative 2 by 7, right? All right, we're gonna kind of let that one be. How much time? Okay, we're just about done. The timing actually worked out. Simplify. Okay, let's give these a go. I think this might be the last. This is the last example. Okay. So let's work on part A. And the timing is actually good. We got like a solid 5 minutes remaining. So we have 5 times 2x to the power of 3 by 4. Simplifying rational exponents. 3x to the power of 1 by 5. Okay. So we should be able to add those fractions, right? If we say x to the 3/4 times x to the 1/5, then it should be 3/4 plus 1/5, right? So 10 times 3 is 30. X to the power of 3/4 plus 1/5, right? So we just need to do that calculation. I'm going to do that over to the side. So then 3/4 plus 1/5. We need what, a common denominator? So look like it's a 20. So we're going to multiply this by 5 over 5. This one by 4 over 4. So then that gives us 15 over 20 plus 4 over 20 to give us 19 over 20. Okay. So then it looks like we're going to get 30x to the power of 19 over 20. And you can use your calculator, but you got to be able to keep it as a fraction. I just want to check that one. Yeah, we got it right. Okay, let's do the next one. So then for part B, we got this 16 over 9 to the power of a negative 1/2, right? So a negative exponent moves it to the, basically flips the fraction. So this should be the same as 9 over 16 to the power of a half. Okay. I think these are perfect squares. The square root of 9 is a 3. The square root of 16 is 4. Okay, not bad. So that one we got 3 by 4. Right. I think they flipped the fraction, square root. Right. All right. For those that survived, right? Are there any burning questions before we go our separate ways? Going once, going twice. Forever hold your peas and rice. Okay. So some key takeaways. All of our assignments for the semester are available with the exception of the exams. I'm building the recordings and the PowerPoint lecture slides as we go, so you have to it's kind of harder to get ahead because I haven't made them yet. So I might make some in advance, but generally speaking, I'll probably make them as we go. I would encourage you all to do like a group meet and or seek out tutoring. I put some information in Populate on a free tutoring service. I'm okay if you guys collaborate and work together. I just need each person to submit their own work and make sure that you're learning something. Don't just like sit back and let somebody else do it, because then you never know when you're going to find yourself in a proctored testing environment where you're going to be responsible for this. It could either be in this course, it could be to graduate, it could be at a job, your first job interview, right? So you get unlimited attempts. Just keep trying until you get the score that you want. I can't think of anything else, right? So this week we worked on section 1, 2, and 1, 3. Let me go ahead and make a copy of this available for you all. I'm going to share, send it to Box. Let me make sure it's in the right folder. This is the spring of 24, Morris Brown. This is what's College Algebra 2. The notes updated daily. And yeah, we didn't take any notes last time. Anything written anyway. All right, I'm going to send this here. Okay, so when this bar finishes loading, you'll be able to pull a copy of all the stuff that you saw me writing. You can access the PDFs in Populate. So one of the first links I put inside the dashboard, there's a link that says Daily Lecture Notes PDF box link, right? It's something like that. Okay, so if there aren't any burning questions, we're going to go ahead and end the session here, and we'll meet next week, same time, same place. Have a great weekend, ladies and gentlemen, and take care. Peace.